Now let's see the kinetic gas equation. Here we will derive the kinetic gas equation with the help of the postulates of kinetic theory of gases. That is, the gas molecules are considered to be individual particles. They collide with one another and with the wall of the container, and the collision is perfectly elastic. Those postulates. We have already discussed about 7 postulates of kinetic theory of gases. Now here we are going to derive the kinetic gas equation, and that equation is very important because with the help of that gas equation we can derive some other equations as well, and all of these formulas are very important for your examination, as well as these are important for numerical problems as well. So let's start the derivation of the kinetic gas equation. Now for the derivation of kinetic gas equation, we need to consider a three-dimensional box. Okay, we are considering a three-dimensional box. So let me draw a three-dimensional box over here. Three-dimensional box, and three sides of this three-dimensional box, that is this side, and this side. They can be considered to be x direction, y direction, and z direction, or simply x axis, y axis, and z axis. Now let us consider let's consider there is a particle over here somewhere in the box. Now its velocity or its direction can be resolved into three different axes. That is, if the particle is moving in this direction, it is moving toward x-axis. If it is moving toward this direction, it is moving toward y-axis. And if it is moving up with this direction, then this is moving toward the z-axis. Okay, and let us consider this is phase A and this is phase B. Okay, and not only that, this is a cubical box, so we can consider the length of the sides of the box to be L. This is a cubical box. This is a cubical box of the side L. So let let the the length of the container is L, filled with gas molecules having mass m. So mass of mass of gas molecules is equal to m, and total number of gas molecules is n. So we have considered these three terms, and similarly the molecules are moving randomly in all direction with a velocity. The velocity of gas is equal to v. So these are the three different considerations that we did. Now if the molecule is traveling with a velocity v and it has certain mass as well, and if it goes and hit the phase A, then it will exert certain pressure over here, right? So the pressure is given by, so the molecule, that is the gas molecule, exerts certain pressure on the wall of the container, given by so what is the formula of pressure? You already know. Pressure is equal to F by A, force per unit area. Let's consider this to be equation number 1. For the simplification, let us consider the molecule is moving towards x direction, that is x axis. We are not considering y-axis and z-axis right now because that will make the solution little bit difficult. So we will talk about x-axis only to make the solution simple, and later we will include the velocity of y direction and z direction as well. Right now we are considering the velocity in x direction only. Okay, so if the molecule is considered to be traveling in x direction with velocity vx, and the mass of the gas molecule is m, then it will have certain, it will have certain momentum as well, right? So the the momentum, so the momentum of the gas molecule, the momentum of the gas molecule having having mass m and traveling in x direction, traveling in x direction with velocity vx is p is equal to what? mvx, right? So this is the value of the momentum. Now if this molecule comes here and strike this A, and it will bounce back because the collision is elastic, so it will again attain some velocity, right? Here we are considering elastic collision, so the velocity will not change. Now as the direction is changing, initially the molecule was traveling in positive x-axis direction, now it is traveling in negative x-axis direction, so we will take the velocity to be negative vx. Now this negative sign only indicates the direction, that is it is going in negative direction. So initially the gas molecule a, had a momentum of mvx. Now after collision the gas molecule will have reverse momentum, right? So after collision the molecule's momentum is minus mvx. So change in momentum, del p. Del p means change in momentum is final momentum. Final momentum is this one, right? So minus mvx minus initial momentum. Initial momentum is this mvx is equal to, it will be minus 2 mvx. So del p, that is change in momentum. Change in momentum is how much? Minus 2 mvx. Let's consider this to be equation number 2. Now let's move forward. Now for a total of n molecules, the change in the total change in momentum, is del p is equal to minus 2 mvx, that is for one molecule, and for total it will be multiplied by n, so it is minus 2 m n vx. Let's consider this to be equation number 3. I hope this is very simple till this point. Okay, now we know that the force exerted by the particle on the wall, total of n particles on the wall, is given by, that is force is equal to change in momentum, per unit time, is equal to del p by t. So the force is given by del p by t, right? Okay, let's put the value of del p. What is the value of del p? From equation 3 it is minus 2 mn bx by t. This is the formula for force. Let's consider this to be equation number 4. Now look at here. So The gas particle will collide with phase A. Now, to collide with phase A again, it will have to travel back from A to B, and again it will have to come back from B to A. So the total length travel by it will be 2L, right? So the total length traveled by it will be 2L. So the time taken, the time, so the time taken by the molecule to hit or collide with phase A again, phase A again is time is given by total length, total length by velocity. The time is given by the total length by velocity. So what is the total length? It will have to travel 2L distance, right? And velocity means Vx. Let us consider this to be equation number 5. Now let's put the value of t from equation 5 to equation number 4. Then what will we get? Using 5 in 4, we get, so using 5 in 4, we get, you can see over here, F is equal to minus 2 mn Vx by t, right? So it is F is equal to minus 2 mn Vx by t. T means how much? 2L by Vx. So it is equal to minus 2 mn Vx square by 2L. L will get cancelled, 2 will get cancelled out, and it is minus m into n into Vx square by L. So we get this equation. Let us consider this to be equation number 6. Now let's move forward. Okay, so this is the value of force. This is the value of force for the molecule. Now with the same force, it will hit the wall A, right? So therefore the force experienced or exerted on the wall, therefore the force exerted on the wall is, so therefore the force exerted on the wall, that is F wall. The force exerted on the wall by the molecule will be same, m into n into Vx square by L. Here we are neglecting the sign because sign only shows the direction, and for wall there is no direction, right? So this is equation number 7. I hope you understood properly till this much. Now if you have force, we can use the formula of pressure, right? Now, the pressure P is, the pressure P is given by, what is the formula of pressure? From equation 1, P is equal to F by A. We have the formula of the force, that is N into M into Vx square by L square. Let's take this L to denominator, and it will be N into M into Vx square by L cube. And L cube, what is L cube? Volume of the container, right? Vx square by V, where this V is equal to L cube. So we get P into, if this V comes to left side, PV is equal to N into M into Vx square. Vx square. This is equation number, what was the equation number? 8. This is equation number 8. So we get the left hand side. Now we need to do the work of the right hand side. Here we have velocity Vx, right? We only consider the particle to be moving in x direction. But does the particle only move in x direction? No, the particle moves in all three directions, right? So the velocity, that is random, the velocity or random velocity of molecule is given by V is equal to Vxi plus Vyj plus Vzk. So this is the velocity component. I, j and k are unit vectors. So if we want to find out the scalar quantities, so we have to take the square. This will give us Vx square plus Vy square plus Vz square. Now we know that as the molecules are moving randomly, then the average velocity in x direction, y direction and z direction will be same. So as the molecules are moving randomly, so we can consider Vx square is equal to Vy square is equal to Vz square. So if you put the value of Vy square and Vz square in terms of Vx square over here, then what do we get? V square is equal to 3Vx square. Therefore, Vx square is equal to how much? 1 by 3 into V square. Now let's use this Vx square into equation number 8. Using this in equation number 8, then what do we get? Pv is equal to 1 by 3 into n into m into Vx square, or sorry, no, V square, n into m into V square. This is the kinetic gas equation. Now this is the required equation called the kinetic gas equation. This is the required equation called the kinetic gas equation. I hope you understood everything about this derivation. This is very important derivation. So understand it line by line and try to learn this as quickly as possible. That's all in this video. If you like the video, please share this video as much as you can. And thank you for watching the video. And please don't forget to subscribe my channel as well. Bye bye.